Okay, so we start talking about the Internet Protocol, IP. Now we talk about datagram format and addressing. Now it is a good time to talk about network address translation and IP version 6. So let's start with NATs. All devices in local networks share just one IP version 4 address as far as outside world is concerned. So this is the idea in network address translation. So instead of giving a global IP to all of these devices, we actually locally use some IPs, but from this world, the outside world think that we have only one IP address, and that is the IP address of the router. So datagrams with source or destination in this network have 10.0.0.10 for address for source destination as usual, but this is the IP address of the router for this subnet. But from the outside world, the IP address of the router is this, and actually every computer inside actually goes to the outside, the rest of the internet, they use this IP address. So all datagrams leaving local network have same source NAT IP address as this one in this example, but different source port numbers. So looking at these port numbers, actually the router knows which data is sent to which host. That is the whole idea. All devices in local network have 32-bit addresses in a private IP address space like this that can only be used in local network. Advantages: just one IP address needed from provider ISP for all devices. Can change addresses of hosts in local network without notifying outside world. This is also useful when we have experiments in in your thesis or projects and so on. Can change ISP without changing addresses of devices in local network. Security: devices inside local nets not directly addressable, visible by outside world. This is the good thing. So this causes more security. Implementation: NAT router must transparently do the following: outgoing datagrams, replace source IP address, port number of every outgoing datagram to NAT IP address and new port number. So this is the thing that outside world sees, right? But this actually, some people against this idea because you're actually modifying the data here, right? So remote client servers will respond using NAT IP address, new port number as destination address. So what I meant was that since you create a port address here for this host, actually the outside world will see this port number. But generally we use port numbers, recall it, at the transport layer, right? Not in the network layer. So you are using it as a network layer to determine the hosts. So you are actually, if you are, for instance, if you are using a port that is specific for a specific purpose, service, now since the new port number will be something different, the outside world will not be, understand what service you are using. Okay. So also this NAT has to remember in NAT translation table every source IP address port number to which NAT IP address new port number they mapped it. So they have to keep it in a table. Incoming datagrams: replace NAT IP address new port number in destination fields of every incoming datagram with corresponding source IP address and port number, again stored in NAT table. Of course, here you are doing a lot of processing, but this, as you can see, really fast. You're just looking at a small table and just modify the IP address and the port. So here's an example. For instance, this device is going to connect to internet and with this destination IP. Now router actually, as the source IP address, changes this, right? So this means that this local IP address with this port will be mapped to this global IP address with this port, which is generally randomly created, okay? So you receive the packet and you modify the destination address according to this table and do the following. So yes, NAT has been controversial. Router should only process up to layer 3. Here we are doing at the layer, above it. layer 4 if you're counting from bottom to top. Address shortage should be solved by IP version 6. Wireless end-to-end argument, port number manipulation by network layer device. NAT traversal. What if client wants to connect to server behind NAT? So this is actually what gamers had to do manually beforehand when they wanted to connect to somebody using TCP/IP, because since the computer they want to play the game with does not have a global IP, writing their IP wouldn't allow them to play together. So you have to do some port forwarding and so on. But NAT is here to stay, so we are not going to leave it. Extensively used in home and institutional nets, 4G, 5G cellular networks, and so on. So at home, most probably we will be using it for a very long time, at least. IP6 motivation. So initial motivation was to, get rid of this 32-bit address space and increase it, because at some point people thought that it will be allocated completely. And some people thought that it will happen around 2008. Some people thought that it will happen around 2016. But in reality, it happened in 2011. So another motivation, speed processing forwarding, because this time we don't have a variable length header, but we have a fixed length header of 40 bytes. Enable different network layer treatment of flows. So here you can label, they are not explicitly defined in RFCs, but you can label different flows and prioritize them and so on. So as you can see, the IP version 6 datagram format is a little bit simpler than IP version 4. Now the source and destination addresses has 128 bits. Flow level, as I mentioned, is used to identify datagrams in same flow, and concept of flow not well defined. Maybe you can define the Zoom communications as a different flow and so on and so forth. So, for instance, if you are watching a movie, streaming it, you might say that it's a different flow, and you may prioritize it. Also, we have priority here. Identify priority among datagrams in the flow. So this is in the flow. So this flow is like a general classification. What is missing compared to version 4? No checksum to speed processing at routers. As I mentioned, since every router modifies the time to leave, they also have to recompute the checksum. No fragmentation reassembly. So if the datagram is large, that is fragmented at the end hosts and reassembled again at the destination. So this way, routers are not troubled with fragmentation and reassembly. No options available as upper layer next header protocol at router and so on. So these are the good things about IP version 6. This is why it is a little bit faster. So question, why haven't we transitioned from IP version 4 to IP version 6 since it's good and so on? So not all routers can be upgraded simultaneously. No flag day. So we cannot say that after this point on, we will not allow IP version 4. Everybody in the world should use IP version 6. We cannot determine such a date because this is a very huge network and there are old devices and so on. You cannot determine such a date. So how will network operate with mixed IP version 4 and IP version 6 routers, right? The question is this. The answer is tunneling. Because, if you have an IP version 6 router, they know what an IP version 4 datagram. But the converse is not true. IP version 4 routers will not understand a IP version 6 datagram. This is why we use tunneling. So IP version 6 datagram carried as payload in IP version 4 datagram among IP version 4 routers. So this is packet within a packet. Tunneling used extensively in other contexts like 4G and 5G. So what you do is just, put the IP version 6 datagram as the payload of IP version 4, then put headers for the IP version 4. So as simple as that. So you make another encapsulation actually. So yes, IP version 6 headers will be inside the payload. So tunneling and encapsulation works like this. So if everybody is compatible with IP version 6, you simply, Ethernet connects to IP version 6 routers. But if there are IP version 4 routers inside the network, since these IP version 6 routers support IP version 4, at this point, you do the packet-in-packet modification, but now your destination will be here. After that, that packet will be removed and IP version 6 packets will be sent here. So, this is how the tunneling works. We already mentioned this, so I'm passing this. So, yes, here is a logical view and physical view. Logically, it works like as if you have a tunnel here and your version 6 packets reaches this version 6 router. But in the physical view, maybe there are IP version 4 routers inside. So here, what happens is as follows. As you can see, now A wants to send data to B. Actually, our destination is F, right? But from this point on, we will use IP version 6. So it looks like we are going data to B. Because at the router B, they take this IP version 6 datagram, put it inside as a payload of IP version 4. But now look at the source and destination. Now the source looks like B and destination is E, right? Because at the destination E, the router will remove this IP version 4 packet and take this IP version 6 packet and send it to F, because there the destination is F. Yeah, not source and destination addresses. This is how we deal with tunneling in real world. So IP version 6 adoption is actually processing really fast. Google says that 30% of their clients access services via IP version 6. NIST says that 1/3 of all US government domains are IP version 6 capable. So you can see that 1/3 of the world actually moved on to IP version 6. Probably in the following years, this graph will come very close to 100%, and at some point on, we will get rid of IP version 6, IP version 4 routers, which will be old at the time. And you might say that, there's a ambiguity here. Recall that in IP version 4, we represented the IP addresses with 4 bytes. So some people think that IP version 6 represent them as 6 bytes, but actually we represented with 8 bytes, right? 128 bits. Here, the numbers actually represent the version. So you might ask, what happened to version 5, right? So it didn't work. So there were planned of a different protocol. I think the name was ST2, but it didn't work out, so we are not using it. So this is why we are moving from version 4 to version 6. Okay, there is no deployed version 5. So it will take long time for deployment and use 25 years and counting. Think of application level changes in the last 25 years, right? In the application layer, we had, web pages, social media, streaming media, gaming, telepresence. So in the 25 years, we updated many protocols, we changed many things, we produced new applications. But at the network layer, as you can see, transition from IP version 4 to IP version 6 takes a lot of time. And this is mainly because, at the top layer, at the application layer, we are doing it with the software and it's easier to do that. But here we have to deal with the hardware, which takes longer time to replace them and so on.